Okay, good afternoon, ladies and gentlemen, and welcome back from the lunch. It's my great pleasure to start this workshop session for today in this conference. My name is Simo Hostikka. I come from Aalto University in Finland, and I've been investigating this topic of today now for a few years, giving some talks, and luckily meeting people from this organization who then very kindly invited me to come here and give this workshop. I understand the idea of workshop is that we interact more than in the traditional or basic lectures. So I hope we manage to do that. I have a lot of stuff to present, but I hope that you are eager and brave enough to stop and comment. I also want to hear your experiences, if you agree or you don't agree. I started as a fire researcher in 1997 when I went to VTT Technical Research Center of Finland to work as a research scientist. For most of my career, I have been working on fire simulation or fire modeling technologies in general. Since 2000, I have cooperated with NIST, developing FDS program. Now, since 2014, I have been working at Aalto University in a position of Associate Professor of Fire Safety Engineering. Today, as I said, I'm going to talk about the fire-induced pressures and smoke spread in airtight buildings. We have had talks, presentations about this subject, and actually even this year, today, we have some wonderful posters about the same subject. So clearly, I'm not the only one. We are not the only group doing research on this, and therefore I expect that there are a lot of experiences also already there in the audience. So we focus on overpressure and what are the consequences of overpressure, and smoke spread, which is one of the consequences that are caused by fire. So it's something that is a result from fire taking place in airtight buildings. And this presentation consists of few sections. In the first sections, we will take a look at what we mean by airtightness. What are the definitions, how it's measured, and what is the reality in our building stock. The next section is going to focus on the experiences, both real incidents, experimental campaigns, and in this section in particular, I'm going to ask you, have you observed these phenomena in your work? Then we will take a look at structural consequences of overpressure. I will briefly introduce what kind of modeling we do, really briefly, but we will focus more on how we use the modeling to extend the experimental observations. And in particular, when we start to look at possible means of managing the overpressure. So the objectives for this workshop are that you will recognize the possible conflict between airtightness and fire safety. You will also be able to identify some solutions, or at least will identify what is my proposal, and you understand somehow what is the scope of assessment, what we can model, what we need to do experimentally, and what are the challenges over there. So airtightness obviously is promoted by the EU level energy efficiency requirements defined in these directives, Energy Performance and Buildings Directive and 2012 Energy Efficiency Directive. And these directives talk about sometimes the energy efficiency in a very vague level. They try to be very, they try to cover the buildings as widely as possible. But when we go to look at the practical definitions, we can clearly see that there is this history of passive house concept which originated at basically at 1980s. That's strongly there on the background, the idea of passive house, which in practice meant requirements or proposals for the use of renewable energies, thermal insulation, effective windows, and regarding the topic of today, the airtightness, for which they had a clearly numerical limit. The air leakage air change rate should be less than 0.6 changes per hour. And then the efficiency of ventilation system. The EU directives don't really talk about passive house, but they introduce the concept of nearly zero energy building, which builds on passive house, but adds aspects like local energy production and energy storage into the picture. But today our focus is in airtightness. There are basically 2 or 3 different numbers that we use to characterize buildings, how airtight they are. The first being called N50, air changes per hour, meaning how much leakage goes, how many times the leakage through envelopes will change the volume if the pressure difference between inside and outside is 50 Pascal. Another quantity is air leakage rate per area, or permeability, called Q50, which is calculated as leakage flow rate divided by the surface area or envelope area. And now here we have slightly different definition between different countries. Do you know your country's building code, using which number it's actually going to define the air tightness requirement? We have 3 options. We have the air change per hour, N50. We have Q50 defined using the entire envelope area, or we have Q50, or sometimes called W50, if that's defined using the floor area. So, how many of you actually know what is the definition in your building code? Okay. Not so many. Okay. Well, it's okay, because luckily Q50 and N50 numbers are usually quite close to each other due to the fact they are defined. Of course, the aspect ratio, the shape of the building is going to affect a little bit what the numeric values are, but anyway, they are slightly different in different countries, and this makes it a little bit difficult to compare the countries. I tried to compose a comparison of Nordic countries. In Denmark, Finland, Norway, and Sweden, I see that the strict requirement for Q50 values is somewhere between 2 and 4 cubic meters per hour per square meter of envelope. The recommendation level, and in some cases actual requirement, is somewhere closer to the passive house level, you remember, 0.6. if we look at the buildings, what is the reality? Of course, our building stock consists of buildings of different ages. And in a study by Juha Vinha from the Tampere University of Technology, they looked at about 100 different timber frame buildings, normal, mostly single family houses, and they observed that the air tightness values now given either as N50 or Q50 range from something below 1, which is the kind of the target level, up to about 10. So there's a factor of 10 variability in the how airtight the buildings actually are. A Danish study showed clearly how the building year affects the airtightness. They had much smaller sample of buildings, but basically going from 19th century building down to something built in 2005, 2007, the Q50 value has come down from something above 10 to close to 3, 4, 5, something like that. When new buildings are made, they are often measured in terms to give them a proof of energy efficiency. And then we can actually look at the data, what the companies making these studies actually collect. And in Finland, for instance, I have been collaborating with a company called, whose name is Vertia, and they publish their own statistics of buildings for new single-family houses built during the last 3 or 4 years. The mean value of Q50 is 1.1. It sounds pretty good, but it's clearly above the recommendation level of nearly zero energy. Some buildings actually reach that objective. For apartments, it's actually easier to achieve the good airtightness because per single apartment you have less envelope area. And the mean is actually 0.6. So these are new buildings. And these are like normal, no special group representing some kind of attempt to or testing or research, just normal buildings that have been built during these years. Okay. Now let's take a look at how this thing started. First kind of incident that I have heard of related to the fire-induced pressure and the hazard that it resulted in took place in Cologne in 2013. Fire took place in an apartment or a house. Actually, it was a passive house type building. It took place in the middle of the night. The person woke up, first tried to put out the fire, didn't manage to do it, then tried to escape through front door, didn't succeed, couldn't open the door inwards. To open it, tried to escape through balcony, didn't succeed, waited for a moment, and then was able to open the balcony door. No casualty, but kind of shocking observations. After that, some studies have been made, and even calculations using CFAST, showing that the pressure peak was probably something over 500 Pascal during that fire. Obviously, it's difficult to know what was the heat release rate and so on. Just recently, researchers from the from Belgium published this research in the chemical engineering transactions. Before that, there were some studies, for instance, by Professor Dieter Brein from Karlsruhe, who did first attempts to use engineering methods to understand what happened. This is a video from the Southwest Finland emergency services from their drill. They set up the fire in an apartment building. Close the door. We see that in Finland we typically have double door system. We have both inwards opening and outwards opening door from the apartment to the staircase. This point, they try to get in, but they cannot open the door. And these are firemen of 100 kilos or so. They wait for a moment, listen to the sound, whistling sound, and they notice that the whistling sound goes down. After which they can actually open the door. Do you have similar observation from your work in fire service? If you have, I don't really see anything from here, but wave your hand. Who has noticed something similar? Yeah, can you tell?
Yeah, we had self-locking doors,
Mm-hmm.
but the room was too airtight, so the self-locking doors weren't going closed.
Okay, the locking mechanism wouldn't work.
Yeah.
Okay. Any other? Yes.
Sessions, in shipping container training sessions, when they light the fire and then they try and close the doors.
Yes.
They lean in and push the doors shut because of the pressure.
Okay. In Sweden, they have. It appears to me that they have actually known this secret quite a long time. Lars Jensen from Lund Technical University has been doing research for this topic for 2 decades at least, but they haven't published really a lot. But it dawned to me that in Sweden they are actually quite much ahead in this sense. They have actual requirements that are related to the peak pressure levels, and they have ways to actually manage it. So we got to learn from them, but before that, let's look at what others have done. I have been involved in OECD PRISMA project, which is one of the nuclear fire safety related research programs. In this program, we have the experiments were made by French researchers at IRSN in close to Marseille. They have a facility called DIVA, which represents a nuclear facility with very airtight containment, and there we have measured peak overpressures of several thousand Pascal. We have observed how the pressures can change the ventilation arrangement entirely. It can reverse the flows. It can change well-ventilated room into a oxygen-limited room because the inflows have been blocked, and so on. But it has been difficult to apply these results to normal buildings because the facility is quite special. Charles Fourneau made a study, and his colleagues made a study in 2012 looking at the safety of passive house, and they actually identified the phenomenon of high pressure and as a consequence the effect that the transverse ventilation flows. Inflows were turned outflows due to the high pressure, but they didn't realize that this could actually be a risk for opening doors or something else. A bit later, Brecht de Provere did his master thesis at Kent. David van Haverbeckere did also master thesis in, it was an international program thesis, and these theses, they have started to measure pressures in different small or medium scale experimental facilities. Irina Karavita did her thesis as a collaboration between University of Mons and University of Bologna, and they are now using the Belgium experimental results from Belgium. Our research project on pressure started as a consequence of the video that you just saw, and we did our experiments in apartment buildings, built in 1970s. It was going to be abandoned because there were some problems with the structures, but it was in pretty good shape. They had renewed the windows quite recently, and we can see that if we measure the air tightness values, Q50, it was less than 2 cubic meters per hour per square meter. If measured in under pressure mode, in over pressure mode, it was slightly higher, 2.7. Okay, what we learned from here first of all, is that the air tightness, which is relevant for us, the overpressure mode, is going to be different number than the number used in the energy kind of label or something of the building. How air tightness, what is the air tightness of the building in normal situation doesn't necessarily give a good idea. It gives a good order of magnitude, but it's not exactly the same number than we would observe during fire. Okay? Oops. So we did experiments in 3 different configurations, so-called normal configuration, where we had ventilation ducts equipped with the normal equipment. Then we opened the ventilation ducts entirely, and then we also closed them entirely. We used 2 different fire sources, a pool of heptane, about 3 liters of heptane in a 0.7 meter square pool. The fire starts and develops in ultra-fast manner, reaching the peak heat release rate of about 800 kilowatts in about 60, 70 seconds. And there's going to be burnout at about 180 seconds due to the lack of fuel. It did not become oxygen limited in these fires. The second group of fires consisted of polyurethane foam mattresses. 2 of them burned in living room, 1 in closet. Also developing in a ultra-fast manner, reaching a peak heat release rate close to 1 megawatt. These measurements were made using the load cell. We didn't have actual heat release rate measurement possibility in the apartment. Okay, here are pressures inside the apartment in the heptane pool fires. In the 3 different configurations of the ventilation. And each curve is an average of 2 or 3 repeated experiments. We see that the pressure develops, first of all, very quickly. We reach the peak pressure in about 20, 30 seconds after which the pressure starts to decrease. Please note that the heat release rate peak was here. So the pressure peaks before the heat release rate and then starts to decay. Anyone has an idea why? Why they don't peak in the same time? I was hoping somebody would. I have an idea, but it's pretty difficult to understand. It is related to the fact that the pressure increase is fastest when the average temperature of the room increases most rapidly. When the fire starts, there's the most energy gain by the gas phase. As soon as we have created a hot layer, we start to, first of all, we start to have heat losses to the surfaces. So we not only have a source term, we actually have a drain of energy away from the gas phase to the boundaries. And also, when the average temperature increases, the relative increase of the absolute temperature is going to slow down. So the positive term source of gas pressure is going to decrease over time, while when the pressure increases, the leakage through the envelope and through the ventilation is going to increase. These two things balance, source and the drain. Source is going to decrease and the flow through the envelope is going to increase, and therefore we have the peak there. Then over here we have the burnout of fuel after that sudden negative peak of pressure. And we can see in the measurements of ventilation duct flows, we can see how here all the ducting is going to flow out from the apartment, and over here all the flows are going to be inwards. This is a test from one of the polyurethane foam tests. Now the fireman who ignited it tries to get out, but he cannot. He cannot pull the door open from the handle. So the fellow workers try to help him and finally manage to open the door. Okay, at the time when he was pulling from the handle, the overpressure in that room was already about 500 Pascal. What do you think would be a good safety criteria for the pressure? Who thinks we should be able to limit pressures to less than 100 Pascal? Hands up. Okay. Who thinks 200 Pascal is good? Okay, thinking we have a door of about 2 square meters. Okay, about. So 100 Pascal means we have how many kilos? 10 kilos per square meter, 20 kilos to the handle. Okay, well, it's not much, and obviously this guy should have been able to pull 20 kilos, but maybe a child, elderly person, someone who is not as sturdy as him, maybe the 100 Pascal is actually a good level. It may be a bit conservative, kind of safe side somewhere, but I don't know. In the pressurization systems, we have requirement of how much? The British standard says and then to the European standards, it says 50 Pascal is the pressure limit. Okay? In 2016, a fire took place in Helsinki where they had some stuff in sauna that ignited for a reason, I don't know at the moment, in the middle of the night. Mother of the family woke up. We know that she has opened the door, inwards opening door. She has entered the staircase. Then, for a reason or another, she has returned, and the reason is that there were the three children. The mother and the children never escaped the apartment. We know they have been at the door, they have been at the balcony door, which also opened inwards. We don't know if the overpressure really was the reason why they didn't open the doors and escape, but they never did. There are signs in the doors. Also, the soot flow patterns outside the door are exactly like what we saw in our experiments, indicating that the overpressure was of the same range. There was the same kind of flow of sooty gas from the gaps of the door. As a consequence, inwards opening doors in the apartments of Finnish buildings have been abandoned in the building code from the beginning of this year. It required one national research project. European observations were not enough. We needed a Finnish study. And we needed a terrible incident which was potentially caused by this phenomenon. Okay. I'm sorry we were a bit too late with our research to help these people, but this is how fire regulation usually works.
Can I ask a question?
Sure.
Having doors opening to the outside could introduce another risk, and that's the risk of blocking from an unknown source that is outside the apartment or the dwelling.
You are saying that outwards opening doors could introduce another risk of what? Can you repeat?
Of being blocked by an outside object.
Okay, being blocked by something outside. Yeah, okay, that's obviously true, and I don't actually know what are the reasons why doors tend to open in different directions. But we also have always outwards opening doors in the apartments, but we have traditionally have double doors for the acoustic reasons. So there's the main door opens outwards, but then there's another kind of cheaper door opening inwards. And that's almost entirely for acoustics, to separate sounds from the staircase. But not anymore. But I know that in many countries, all the doors usually open inwards. Okay? Structures. I had this photo from fire department of city of Tampere. What we see, it's a small apartment of a first floor. We see that there has been really heavy flashover fire consuming basically all the combustible. We see plain, clean, nice concrete surfaces. Even the soot has been burned away. What's here is the out wall element, which is kind of lightweight element with wood frame, wall element, window element, and it has been attached to the concrete element structure. there are no burns, no fire damages in these structures. They have not been charred. They have not been even severely heated. So this thing has come down from the wall before it really got hot. And it probably got really hot because it came down, providing a lot of air. Mm-hmm.
Like window was down.
Okay.
I don't think there is a big fire necessary to have this effect.
Right.
I was puzzled, how can this happen?
Yeah.
Mostly was because the window wasn't attached to the sides and just with the new custom expansion foam into the spine.
Okay. Okay. So he was saying that he has seen a window being pulled out. Maybe at that time not really being able to, you were not maybe able to explain what had happened, but clearly even small fire had been able to cause that. Okay. In the research field or the fire resistance studies, again, French nuclear fire safety researchers have studied the performance of fire doors and dampers under different pressure differences. They have a huge facility called Starmania for this purpose, and they have been measuring, but unfortunately publishing very little. They have some publications shown there which tell that for fire dampers, they have observed them to fail due to the pressure difference when the pressure differences are order of 15 kilopascal, 15,000 pascals, if the pressure difference is in the nominal direction of the flow, or more than 50 kilopascal if it's against the normal flow. For fire doors, like the one shown over here, they have seen that failures can take place at less than 2 kilopascal, 1.7 kilopascal, in the direction that the door normally opens, or something like 8 kilopascal if the direction is against the opening direction. Okay, first of all, quite wide range. High pressures needed for small things like fire damper. Few kilopascals needed for doors. This is another polyurethane foam test in our experiments. Now the foam was in the closet. You see the pressure on the top, on the right, more than 1,000 pascal at the moment, going down for a moment, then increasing again. They say that smoke is leaking through the wall to outside. We didn't expect that. Does it look familiar? Right. You didn't see the smoke. Right. What happened was the frame, window frame, being pulled out from the wall. Glass did not break first, but the frame just came out. And the pressure, when it happened, was something between 1,400 and 1,650 pascal. Again, the construction workers had been a little bit quick. They hadn't used screws. They just used the polyurethane to fix that window frame in place. or at least that it wasn't properly attached using screws. That can happen. Now let's look at the modeling. We have used two different types of modeling. First, FDS, carefully modeling our own experiments, and then another campaign that was conducted by the Swedish Defense Research Organization, FOA. Using the FDS validation methodology, using which we can measure the model uncertainty or model accuracy. For this test, for the prediction of the peak pressure, model bias was 0.95, telling that in average we underpredict the pressure by 5%. Quite okay. And the standard deviation was 24% of the pressure. Then, FDS calculations were pretty time consuming to do really wide range sensitivity study. Therefore, we made another simple model, which simply assumes that we have a homogeneous gas phase and we have leakage through the envelope. Using the FDS models for the thermal environment, we can make a simple analytical equation that tells how the pressure is going to develop if we change the leakage. We need a good fire simulation model like FDS to tell how the temperature develops, because the temperature increase gives us the pressure gas expansion source term for the pressure. When we have that, we can change the air tightness in the analytical model pretty freely and see what would be the pressure if we have different envelopes. And again, we did the validation for this model using the same data set. We defined a scenario of a apartment building, one floor of apartment building consisting of apartments of 50 to 100 square meters. We investigated 3 different levels of air tightness called traditional, modern, or near zero, having Q50 values of 3, 1.5, and 0.75. The model includes the inflow and outflow ventilation networks with fans, possibly dampers, and so on. What's difficult to model is accurately model the wall structures and leakages, because normally the airtightness measurement for such a building is made for the entire building. So we don't really know how airtight are the internal walls. Also, when we have dampers here, we in the model, they are kind of ideal. They are either closed or open, but there's nothing in between. And real dampers are not that perfect. Okay? We did measured the simulated peak pressures in many different configurations with different fire growth rates. Let's look at the results from the fast T-square fires. We have 3 different configurations of dampers. Here we don't have anything, no dampers, open ducts, and ventilation working. Here we have closed the inlet duct, and here both ducts are closed. So some clever fire engineer has decided, okay, we actually put fire dampers there to protect neighbors, so we isolate the apartment, and we see that we get the highest pressures. There's huge difference between the 3 building types, traditional, modern, or near zero. Near zero level would give more than 3,000 Pascal if we have both ventilation ducts closed. Clearly, we could expect structural damages. If that's outer wall, okay, it was quite dramatic, but doesn't necessarily cause immediate danger for the neighbors. What if the failing structure is between the burning apartment and the staircase, which we usually assume to serve as an escape route for the other occupants of the building? It means that such an overpressure could cause a loss of fire compartmentation and the usability of escape routes. Nobody has so far reported that, at least I haven't heard. Anyone here? Okay. On the other hand, we see that with the fast T-square fire, all the scenarios have peak pressure which is higher than the 100 Pascal that we just voted to be the safety criteria. It means that no matter how we defined our ventilation system, we cannot provide safe escape. However, there's great difference, or actually in only one of the scenarios we would expect structural failure. Last year, Ruud van Herpen, who unfortunately is right now giving another workshop, had a presentation here. How many of you remember? How many of you was here and remember what he said about his research? They had been studying a fire in a fairly small compartment and looking at the pressures in configuration where they had closed the ventilation and opened it. What did he say? How many was here? Nobody wants to tell. That you were here but don't remember. Well, it's hard to remember such details. But actually there's one poster from the group also today here. And what they noticed that opening the ventilation system that didn't make much difference. It couldn't provide safe escape conditions. On the other hand, Jes Grotum Nielsen from DTU made his master thesis where he took our modeling scenario, modified it to comply with the Danish ventilation design standard. What he saw that with different fires from slow to ultra fast, in most cases, like the pressures were quite close to 100 Pascal. And his conclusion was that actually using the Danish standard ventilation ductwork can pretty well serve as a pressure relief path. Okay, what we learn that it depends on the sizing of the dimensioning of the ventilation system. In their regulation, the design guide, they clearly have bigger ducts, more volume flow, or bigger capacity for the ventilation system than in the Finnish buildings. Now, for the escape in our case studies, if we take the 100 Pascal as a safety limit, we can see when the escape is possible or when it's not possible. For traditional buildings, the time to reach 100 Pascal starts from somewhere 70 to 80 Pascal, 80 seconds. A bit more than a minute time to escape. After that, you got to wait to somewhere close to 4 minutes until you can escape. Can you hold your breath for that time? Maybe not. Going to modern or near zero buildings, that time that you have available before 100 Pascal is going to go down to less than 30 seconds. Okay, and now we measure the time from the actual well-defined ignition of a fast T-square fire. But those are pretty short times. And fairly long time spans to wait. Using the analytical model, we can now extend the results. We can vary the leakage area, and we see what kind of peak pressures we observe with different apartment sizes. From there, we can pick what is the critical Q50 value that we should have in order to keep pressures less than 1500 Pascal, which we now take the structural safety limit. If I go back one slide, we see that for the 100 Pascal limit, we would need really high leakage areas. I don't go to that now. We saw that it's going to be difficult, and we need some special arrangement. Just the leakage path itself, it's difficult. On the Danish study showed that, okay, maybe ventilation network can do it. But what about the structural safety? For medium fire, we observe 1500 Pascal pressures only in small apartments. If we go to fast fires, 100 square meter apartments show the high pressures, and we need Q50 from 0.7 to about 1, above the passive house level, in order to make sure that structural damages don't occur. If we go to ultra-fast fire development, then it's pretty difficult. For small apartments, we need leaky apartments. Big apartments can be somewhere between 1 and 1.5, which represents the current building stock, yeah, but it's not what we want the buildings to be from the viewpoint of energy efficiency. Okay, smoke spread. In the fire, that incident that I mentioned, they noticed that smoke had spread to most neighbors of the staircase through the ventilation shafts. Doing the modeling with FDS, we looked at what is the smoke concentration in the neighbors in the different ventilation configurations. And we measured the smoke in terms of visibility. This is a visual picture of what we see. We have the fire apartment, basically black, and then some gray stuff in other neighbors. There's only one. Okay, obviously, if we have both ducts closed by damper, then there's not going to be, according to the model, there's not going to be smoke in the neighbors. Also, if we keep the fans operating and we close only the inlet duct, there's not going to be smoke in the neighbors. It means that the smoke spreads mainly through the inlet ducts, the inlet branch. If we have exhaust branch open and fan operating, the pressure differences in the ventilation system are high enough to extract the smoke from the system, and it's not going to neighbors. In terms of visibility values, if we look at the range in the neighbors, this box now represents the visibility values in the neighboring apartments. For traditional buildings, we see that with fan operating and no dampers, the visibility goes down to order of 4. In near zero buildings, it would go down to about 2. If we close the fan, and I will tell what it means, and we have no dampers, the visibilities will go to about 2 meters in all the cases of the envelope. And by fan closed, we mean a scenario where we not only turn the fan off, but we actually assume that the fan closes itself. So basically the entire floor ventilation system became closed system. Expect the envelope leakage. And this is due to the fact that the modern air handling units of the ventilation systems, they have a lot of logic in them, and they have a lot of protection systems and many of them, at least in Finland, operate in such a way that if you turn off the fan, it will actually close the external valves for weather protection. And it will mechanically close itself, which is not a good idea. Okay, so before the fire service requires that, okay, in case of fire, stop the fans, it should make sure how it actually works. In case of emergency, you don't have time to find drawings and logic, operational logic of the air handling units. So it means that in our fire safety and ventilation designs, we should, in cooperation, look at how these things should be designed in order to make sure that they work safely. Jim McGonigal from the Glasgow Caledonian University looked at the problem from the viewpoint of staircase pressurization systems, basically showing that in traditional UK buildings, in order to pressurize the staircase, it was just enough to provide the overpressure. The leakage of the building envelope was enough to provide the relief path. Now, when the envelope is getting airtight, the smoke cannot flow out from the burning apartment, and it will actually flow to the staircase despite the existence of the pressurization system. So in airtight buildings, we need arrangements in the building wall, building envelope, to make sure that there is the path for the smoke to flow out. We are getting to the end of this workshop session soon. I want to go through some uncertainties. First of all, when we model these things, we assume that the leakage volume flow through the envelope behaves according to the simple orifice flow equation. The flow rate is proportional to the surface area, discharge coefficient, and square root of the pressure difference. When we go from the pressure differences that are typical to energy efficiency measurements, few pascals, few tens of pascals, up to hundreds or even thousands of pascals, it's quite clear that the walls are going to change. Gaps are going to open. It's going to move, bend. All sorts of things happened, and the leakage paths are not the same as in the initial condition. How to model that? There are ways to try to include the effect of the pressure in the leakage area, but we haven't used that so far. I don't know how much that is going to change the results. Internal partitions, I already mentioned this. We have pretty good knowledge about the building envelopes, but nobody really knows the airtightness of the internal walls, how it's going to affect the compartmentation, how much of smoke is actually going to flow to neighbors through the walls. I don't know if you have any experience on that. You could maybe share some of it. Sometimes I have heard Finnish firemen to tell that, okay, they saw smoke spread from the electrical plugs. Okay, that happens. But, okay, it's under the walls, yeah. Usually they have been quite minor leakages. You notice it happens, but it doesn't have any safety significance, really. It's not going to challenge the life safety. But, yeah, it's going to affect the pressure calculations. Ventilation system performance and modeling. We have assumed that the dampers are kind of perfect. In reality, they are not. Then there are other paths of leakage in the buildings than the envelopes and the ventilation network. In particular, the toilets. In our experiments, we sealed the toilet in order to avoid leakage through that. But if we have 5 centimeter height of water here, 500 pascals would flush the toilet, possibly. And we would generate another leakage path to the sewer system. So it's obviously a good thing. And next time you forget to close your toilet, you can just tell yourself in bed, hey, but it was a good thing. Yeah. Okay. To conclude, we see that even medium fires in airtight buildings can prevent the people from escape, from opening the inwards opening door. And this is clearly something that the building codes must take into account, like we now did in Finland for apartment buildings. Fast and ultra-fast fires might actually, and they can challenge the structural integrity. They can challenge the compartmentation. And this is something that we really haven't considered in our design, our regulations at all. What's that?
You can open the door afterwards. It will open the door.
Yeah, yeah. Yeah, it will relieve the pressures. That's good. Yeah. It seems that we can use ventilation network for the pressure management and to avoid smoke spread at the same time if we use the combination that I mentioned. We close the inlet branch using a damper, which can be a pretty simple damper, it doesn't need to be really heavy duty. And by keeping the exhaust branch open and fan operating. Then it depends on the dimensioning of the system, if it really, to what extent it can provide, or to what extent it can keep the pressures down. Can it really help for the door opening problem? It depends. The recommendation, we must take into account the pressure increase for structural fire safety. This is something that our fire resistance requirements in Europe don't take any stand. We have requirements for temperatures, maybe load-bearing capacity, integrity, but should they actually require some strength against lateral forces? That's something to think about when we think about the fire compartmentation in case of overpressures. What we learned that fire engineers and HVAC engineers should actually work together if we want to use the ventilation system in order to manage the pressures. And also, we need more research on topics like air-tightness of internal partitions and how the ventilation systems actually work at high pressure differences. HVAC engineers know how they design for normal conditions, but nobody really knows how they are going to work if we have 1,000 Pascal or 2,000 Pascal pressure differences. To conclude, I would like to thank sponsors and partners that helped in this research project we had. I have had a pleasure to work with few students, Rahul and Numar, and then I have consulted a lot of people when doing this work, in particular Thomas Fagergren from Sweden and Peter Biström from Stravent, and then Stravent O, and then guys from the Southwest Finland Emergency Services, Knut Lehtinen and Pasi Paloluoma and Pekka Mutikainen from Tampere. Okay, now it's time for your stories, if you have been saving them up to this point. Yes.
You talked about pressure release to the outside, so that means through the facade, or would you prefer to have a ducting system on the outside or a shaft to relieve it?
Mm-hmm.
The moment you penetrate the facade, also that one has to be taken into account when talking about facade systems.
Yes. What I have learned from architects that they hate to even discuss, like, can we put some technical system on the facade to manage pressures? But yeah, in some facade systems that could be quite easy. Yeah. But do you have like actual? How would you proceed?
How would I proceed?
Yeah.
I'm just thinking about this, how to proceed. This is why I came up with the best.
Okay. I don't really have a solution for that. Yeah.
We had exactly the video that you played of the person who set the fire getting trapped in the room.
Mm-hmm.
We had exactly that happen in a training session, and the instructor thought he was going to die. He couldn't get the door open,
Uh-huh.
and then suddenly it just opened.
Yeah.
And we didn't understand why. He thought the door got stuck. We checked the door afterwards. It seemed
Right.
fine, you know, and now I'm going to, as soon as I get out of here, I'm going to be phoning the training centre and tell them. They need
Yeah.
to tell the
Well.
instructors about it. Thank you.
You're welcome. So, if this didn't go to YouTube, I would tell that that was actually an accident. Well, it goes to YouTube. No, they know. But yeah. In our experiments, the people had the breathing apparatus, and in most tests they actually stayed inside on purpose. So there was no problem with it. In this particular test, he was actually coming out from there, but we had the cameras there to see what happens, and it was kind of accident that the door closed before he got out, and we got this video. Yeah. Yes.
Is there enough oxygen to survive the period from getting stuck in the door until it can be reopened again? Is there enough oxygen to survive?
Well, oxygen probably is not the problem, but the other toxic species. In such a apartment fire, if you have medium fast fire, how long does it take for the smoke layer to come down? Experience? 2-3 minutes, yeah. Depends obviously how quickly it starts. In ultra fast fire, in about a minute. In medium fast, a bit longer. That's how long you would have time if you stay down. Then you are going to start to breathe the smoke. So we saw times 2, 3, 4 minutes. Yeah. Yeah, you had some comments.
Question, did you also make a test with the combination of sprinkler and what to do with the pressure? Did it collapse the pressure within
Yeah. Okay. No, in this campaign we did not. Somebody probably has.
The VIPA investigation we yesterday heard,
Mm-hmm.
sprinklers drop the pressure immediately.
Yeah.
I'll take guy over there.
Yeah. Over there.
Yeah, but it was not an ultra fast curve. So, and it was not so airtight.
Mm-hmm.
I think these are two big differences with all what you were discussing.
But
In order to maximum values of overpressure and so on. So we have seen that the overpressure, even with small fires, is 50, 60 Pascal or something, and at the moment that the sprinkler activated, you have the same behavior as the burnout of the fire, meaning that it drops immediately and it gives an underpressure.
mm-hmm. Yes.
So it's more or less the same behavior of a sprinkler as the burnout and the
Yeah. This fall we made another project. We had a sprinklered healthcare center in Finland, and we did. Maybe didn't hear. So you mentioned that you have seen that the sprinkler activation is actually going to cause underpressure or clearly reduction.
It stops the overpressure
Yeah.
immediately.
Yeah. Immediate
Immediately
drop of overpressure. Yeah.
gives even an underpressure.
Yeah. So we did a similar study in patient rooms. We did 30 fires in sprinklered patient rooms, and in almost all the tests, the sprinklers went off in about 1 minute. Up to this point, it was really difficult to keep the door closed to the corridor. The firemen really had to lean on the door if they wanted to keep it closed, because due to the overpressure. At the activation, boom, it was pulled inwards and the pressure dropped. There was a short under kind of peak, but then it was basically kind of stabilizing. So sprinkler caused immediate drop in temperature and negative term for the pressure equation, and in the modeling sense, and pressure was not problem anymore. Anything else? Questions, comments? What about any fire safety engineers, consultants here in the room? How do you think you should consider the pressure in the performance-based design of buildings? Are there situations where it could be relevant? These studies have been mostly apartments, and we saw that the compartment size has an effect. Do you actually do fire consultancy for homes? Or are they always something very big? No? So the actual fire safety engineering projects don't bring this viewpoint into the building home design, apartment building design. It must come through requirements, regulations, and maybe through the ventilation designs. I don't know. Wonderful second workshop for today. Thank you.